Great. Thanks, Shashi. And hi, everyone. I'm Ranjan. I am a data scientist at Julia Computing, and I'm just going to take you through why we would call Julia the language for AI. So the question is, what do you want to do, right, with regard to machine learning? Do you want to crunch data? You want to crunch large volumes of data? You want a very flexible framework with which you could execute different kinds of mathematical operations. You want GPU support, which should be first class, right? Because nobody runs distributed training these days. Everything's done on the GPU, right? Even if it's distributed across multiple GPUs. So why exactly does Julia fit all those various constraints? So first, Shashi actually gave you a decent window into our ecosystem. So we have a robust statistics and optimization ecosystem. So what happens with machine learning is that you have a bunch of statistical models that you're trying to learn via constrained and unconstrained optimization, right? So our statistics ecosystem is extremely robust. We have generalized linear models, decision trees. We have a first-class constrained optimization ecosystem. JUMP, which Shashi used for his previous demos, actually used at a variety of cutting-edge research labs across the world. In fact, people are using people are using it on autonomous vehicles. People are using self-driving cars, for example, performing constrained optimization within small windows of time so that little cars can drift. So the idea is basically is that the ecosystem in itself is first class. So then again you need parallel computing to do machine learning, and then we have Dagger and JuliaDB, which you got a flavor of in the TrueFX demo, and how that sort of fits into your analytics workflow. And we have something that no other language has. We directly generate PTX code that runs on the GPU. So PTX is machine code that runs on the GPU. So for example, we have x86 assembly that runs on your Intel processor, right? So PTX code runs directly on the GPU, and we have that in Julia. And so the advantage with that is that you can specify arbitrarily complicated GPU kernels that can run very quickly on the GPU. You don't need to write CUDA C code for that. And of course, our deep learning ecosystem, I've just given you a couple of examples here. There's one package called KNet, which is your TensorFlow MXNet like deep learning package that's written in pure Julia, and then you have a Flux. That's kind of like you could think about KNet as analogous to TensorFlow and Flux as analogous to Keras, right? And of course, we have wrappers to TensorFlow and MXNet and all the usual deep learning stuff that you have out there. But what I want to focus on right now is why specifically Julia is good for AI. So just to set this context, I'm pretty sure Shashi has shown you some stuff with regard to. Let's see. So he's shown you machine code that's generated on Julia, right? So supposing if I do 1 + 1, right, and this is just simple integer addition, and we can really look under the hood and see the machine code that's generated for this, right? So if you can see that, so this machine code, if you look at right here, this is the right assembly line instruction to do integer addition, right? And let's say we're doing on 2 floating points, all that's happening is that you're using the right machine level instruction for floating point, right? And that's the only change that you're seeing right here. So why is this important and useful? And so to set that context, let's come back to the slides. First, let's talk about a simple vector addition kernel that would run on a GPU. So why is this important? You need your deep learning and machine learning packages to run directly on the GPU, right? So that you get really fast training. And why did you want to run on the GPU? Because most of your machine learning is BLAS intensive, convolutions and everything, matrix vector and matrix multiplication intensive, which run pretty well on the GPU, right? Okay, so now let's take a simple vector addition kernel, and you find that what we're doing here is this is just figuring out the index for that particular thing, and now we're adding these two vectors. So essentially, out equals a plus b. That's how this is written in CUDA speak. So how many of you guys have actually seen CUDA C kernels? have written Q-C? Okay, that's totally fine. So if you want to add two vectors on the GPU, you need to write something. You need to. There's an extension to C called Q-C, which you write on, which you write and runs on the GPU. So that's like a little bit long and complicated. With Julia, that's significantly shortened because it's a high-level language. It's not C, right? So now I have a simple kernel that adds two integers. So just have in your mind a kernel that adds two vectors in C. So that's gonna look like this, right? Out of I equals A of I plus B of I, right? So how do we build up from here? Okay, so in Julia we have something called generated functions. So what this is essentially going to do, it might look a little obscure at first, but what this mechanism is allowing you to do is that you can generate functions like this. So what does that mean? So now I have a simple vector addition kernel. I can now extend that to add arrays of multiple dimensions, n-dimensional arrays, right? So I can make it work for matrices, tensors of all kinds, with the same amount of code that I used earlier, right? That's essential. That's the takeaway from this. And so what's important to note that the Julia compiler is just generating the code that you want it to run and have it and breaks that down into the appropriate amount of assembly code that you wish to run, right? And that's just not happening. It's not like it's just happening on your Intel processor. It's now directly generating that code that would run on the GPU, right? The instruction set, everything about it is completely safe, but that's all of that complexity is hidden from you, the user, right? So there's that. Next. As I said, yeah, vector addition now becomes an n-dimensional add, right? So what's next? Now let's make this code generic. So first, what we did was we added two vectors. But let's say, what do you want to do? Subtraction. What do you want to do? Multiplication. Bunch of other things, right? So instead of doing plus here, you could pass this function f. So this kernel zip2 is something we call a higher order function. Some of you guys familiar with some functional programming paradigms might be familiar with this term. So kernel zip2 is a higher order function where you're passing a little function inside, and that's going to do that operation on A and B and then return out. So what's happening here is so we started off with a vector addition add, and then we generalized it to n dimensions, and now it needn't be an add, we can just do anything we want, right? So again, it's all in the same, it's all in the same, whatever, 4 or 5 lines of code, right? So the power you're getting from writing that 4 or 5 lines of code is what I'm trying to emphasize here, right? So that's the next step. Then what do we do, right? So we get derivatives for free. So what tends to happen in a statistical learning process is that once you've computed your objective function, you're going to want to take derivatives of that objective function with respect to the parameters of the model, right? Which is what you do in all your machine learning. And then once you do that, you sort of tweak the parameters a little and pass it into your unconstrained optimization loop again. So that's what you're going to do. So you need fast and quick derivatives. So how many of you guys have heard of automatic differentiation, autodiff? All right. So autodiff is a nice little, it's a nice little mathematical trick. So for example, so I'm just going to demo this little package to you. Hopefully that compiles. But so autodiff just allows you to take derivatives of arbitrarily complicated functions. So for example, let's say I have f of x equals x squared, right? Let's say I have a very simple function like this. So what am I going to do with this? So I'm going to import something called a dual number. I'm going to define something called a dual number. And what do dual numbers do? So let's say my input is 1, 1, right? So dual numbers you can kind of think of them like complex numbers, is that they have a real part and an imaginary part. Well, but this isn't an imaginary part per se. This is something we call a tiny epsilon, right? So this is gonna look something like this. So this isn't pi, this is epsilon. So what benefits does that give you? So if I do f of 2, I get 4, right? So Julia has just generated the version of the function that runs for integers and is giving you 4, right? So what if I pass my dual number? So let's see. Yeah, so I put in 1, 1. So what it does is the first value here is the derivative. Yeah, so first value here is the value of the function, and the second value is supposed to be the derivative, right? So you can see dual of 1, 2. So again, there is no symbolic, so I'm just going to tell you what it's not. It's not symbolic differentiation. It's just using the code itself and then giving you, and just giving you the derivative of the code at a particular value, right? So what is the derivative of f of x? It's 2x. And what is 2x at 1? It's 2. So that's why you're getting dual of 1, 2. So why is this important? Now, just to step back a bit, what we have now in our toolkit is a vector addition that we've now extended to multiple dimensions, right? And now we've made it a higher order function such that it can do whatever it wants on the 2 elements in the vector, right? And now we get derivatives for free. So what do I mean by for free? There is 0 difference between computing with a dual number and computing with a normal integer. Like performance-wise, it's just 0. There's no overhead to that, right? So what advantages does that give you? If you have a neural network which is just a series of layers, you're going to want to differentiate through that, right? You're going to want to differentiate through that. So what we can do in Julia is that we can have each layer of the network behave as a function and just sort of evaluate the objective function towards the end, which is just a forward pass through the neural network, and then based on the weights and biases in each of the parameters, we can take the derivative of the objective function with regard to these weights and biases, right? And on top of that, it's all running on the GPU for free. So that's the power you're getting from something like Julia. So most machine learning people would have heard of the sigmoid function, and the sigmoid function. Suppose we want to take the derivative of what the sigmoid function is giving you with respect to your input parameters. That's what you're going to get. That's basically the language specific features from the code level downwards. Those are the advantages that Julia is giving you. All right. So let's go code level upwards, right? So in Julia we have something called macros. So if anybody's used Lisp, you would have probably heard of that. They have Lisp-like macros. So what is that? So what macros allow you to do is to write DSLs, domain-specific languages. So jump, as you saw, was something we call a domain-specific language, which says, well, what do I need for a constrained optimization problem? I need to define my objective function, I need to define constraints, and just run the optimization problem, right? So what you're going to do is, what jump allows you to rather, is to say at constraints and just list your constraints, and then do at objective and just list an objective function, right? And to specify things in that manner, that let's say a person who's coming from the place of, I want to solve this optimization problem, that language which he's working in is crafted specifically for him, right? That's a domain-specific language. So similarly, we can write a domain-specific language for neural networks, right? So this is taken from a package called Flux, and what it's doing here is we are defining an LSTM, right? So just imagine you have a newfangled neural network which you're trying to implement from a paper, right? And you have like the mathematical formulae for it in the paper, and you kind of want to you understand that, you kind of want to use that understanding and sort of have that run in code, right? And this, let's say we're doing that for the LSTM, and these are the equations you'd find for the LSTM. And what's happening here is, you can see the Julia function here looks just like the code, right? It's like almost exactly like the code. So that's the power you get. Of course, there's the more superficial advantage with regard to Unicode characters. So you'll have alpha, betas, and sigmas, and all those sorts of things. But the real advantage with the macros is that you can just specify this stuff, and then and then the Julia compiler or the parser will just unroll whatever it needs to be, needs to be unrolled in like in a proper recurrent network, right? So that's what you can do. So here you have a nice little DSL with which you're specifying neural networks, and you're having Julia take that and specify that in terms of functions, and then you have the Julia compiler have that, run that generate just the right code to run on arbitrary number of platforms, right? So that's how this flow is going. Next, so once you define the neural networks, you're gonna want to use them, and since in Julia we're thinking of in Julia we're thinking of neural networks as generic functions with tunable parameters and the parameters are weights and biases, right? So those are your tunable parameters. And what's happening is you're specifying models as generic functions, right? And now you can chain these functions together, right? So you send one vector in, neural network layer 1 takes in this vector, spits out another vector, etc., right? So it's going in this particular order, and this is a simple two-layer perceptron, MLP, which is around. So you have this little function definition, and then over here I'm passing a random vector of length 784, but that could also be a CUDA array, or a GPU array that you're passing in, right? And all this is just supposed to work, irrespective, based on the input type you're giving it, because you've told Julia what to do when you get a GPU array, and it without any compile time overhead is going to generate that code for you, right? So now what do you have now? You have a highly flexible machine learning framework in Julia, and that's so if you kind of look at KNet, you kind of look at Flux, you kind of look at the ecosystem. That's how Julia is kind of shaping up to run as. And in addition to that, we have these amazing pre-processing capabilities and the richness of the ecosystem, of the mathematical ecosystem. And what you have is a language and a set of tools that you could use not just for deep learning, but for analytics or for statistical learning or any kind of scientific computation you want to do, right? So that's basically it. So that's basically the Julia side aspect to this. So what I'm going to do for the next 10 minutes or so is to just show you a few applications, a couple of applications, and for that I am going to take a picture of everyone. So let's see if this works. Just tell me if I've gotten everyone. Let's just work. It's cool. Fantastic. So let's just save that. Export. Cipher.jpg. Go. All right. So that's you guys. So what am I going to do with this picture? I'm just going to run this little thing I have. So I wrote this little package called texturize, and we'll see what it does in a bit. So very quickly, just run this code. So it's just going to do a style transfer, and I'll sort of get to what a style transfer is. I'm pretty sure people already know what it is by now. Like, have you guys used this app called Prisma? It used to be pretty popular like a few months back. Yeah, it's kind of doing the same Prisma thing. It's a neural network. You'll see what happens once it's done. So, all right. So one example of an application that I worked on, this proper deep learning application is. So this disease called diabetic retinopathy, and how you detect that disease is you kind of take these special cameras and take pictures of people's eyes. I've gone through this test every year, and you kind of check whether you have diabetic retinopathy. And what you do is the doctor sort of looks at this and says, well, are there any cotton spots here, or are there any weird weird patterns here, and if so, you have diabetic retinopathy and you need help. Otherwise you're good. So what we did was we took a bunch of we took this data set filled with fundus images, and we wrote a deep neural network to sort of check which ones are safe and which ones are infected and which ones aren't. It's still a work in progress, and I'm still working on it. And the thing is, we've not just taken stock data, we've actually worked with organizations and gotten low-cost fundus images from them, and we've tried training on that. And there's the images, the quality of the images isn't great, plus there's a lot of error and noise in there, and we sort of think about ways to deal with that. And the second application is going to show you, is the neural style transfer. And if you've seen this before, it's basically this neural network model called the VGG model, and the specific variant of the style transfer I'm going to show you now, it's sort of it specifies loss functions as neural networks themselves. So these are called perceptual loss functions. So perceptual loss functions are like, well, suppose you have an image here, right, and you shift it like by 1 pixel to the right, and the error here is going to be just the numerical error here is going to be massive, because hey, none of the pixel values match, right? But the fact is, we see that the image itself isn't errored. So that's how this loss function, this perceptual loss function, takes in these two images and calculates the perceptual loss. So based on that, you get a different kind of style image. So that should, let's see if that is done. Yep. So that kind of neural network is going to give you something like this. Right. So here's that. Then what else do I have? So of course now once we've done it on one single image, we can do it on a video. And I took a little football video because I love football, and I sort of did a little style transfer on that. As you can see, it's happening here. So there's a little fiery texture that's just gone through everywhere. Yep. All right. So just gonna let that video play. But the thing to sort of note is that in Julia, the idea is you could sort of do this stuff easily, right? And not only do these fancy sorts of things, right? So this is just probably for demo value, but you'd want to do scientific computation well, which is what machine learning is all about, and that's what Julia lets you do. And of course, there are other little projects on statistical learning that I'm working on. I'm more than happy to talk about offline, and we can discuss. You can discuss more ways. I can demo more specifics. And let's see, what else do I have? I also wanted to show you this one project which I didn't include on the slides. It's called Celeste. So what my colleagues did was they took this 55, 60 terabytes data set called the SDSS. It's called the Sloan Digital Sky Survey. Yeah, it's called the Sloan Digital Sky Survey. And what we did is they crunched it in about 20 minutes on an actual supercomputer at Lawrence Berkeley National Labs, called the NERSC supercomputer. So what exactly is happening here, right? So what they are trying to do is they have a catalog of images in the sky. Like, so you look at the sky and then what you have labels for each of the celestial objects, right? So the thing is, you don't have a catalog per se, but you have labels for different celestial objects. So what you're doing is you're taking the information that you know, and you're trying to come up with the complete catalog. So you know, for let's say a few gigabytes of labels and images, and you're trying to figure out what it is for, let's say, your 55 terabytes, and you use something called Bayesian inference, an algorithm called Bayesian inference to figure that out. And the thing about Bayesian inference is that it's notoriously hard to do computationally. So you need to do approximations via these techniques called Markov chain Monte Carlos, and then Monte Carlo methods, and then after that, you kind of have to write your own optimization loop, and the loop that most people tend to use is a quasi-Newton kind of method called LBFGS. Though I suppose they wrote their own Newton method, which is probably a variance of that. But what's the takeaway? Loaded 178 terabytes of image data, or it's 178, I'm mistaken, and then they've got 1.5 petaflops of performance on the supercomputer. This is actually the first for a high-level language. Python, R, and all those other languages just cannot do this. The reasons it can't, which we'll get to. And it achieved a performance improvement of 1000x on single-threaded execution, performed complicated Bayesian inference, and not only point estimates for light sources, but a principal measure of the quality of inference. Right? So they have an actual they have a measure for if their work is actually good or not. I'll obviously link this to you guys so you can get more information. So those are the various things that we've been up to with Julia, and I guess that's all I have from my side. Let me just verify that. Oh. Yeah, so I'm happy to take questions at this point. So we have 3 minutes left, I suppose. So maybe we could just take questions. Yes.